Hello, this is the notes for 1.4a and 1.4b. I will make a verbal indication when we're at 1.4b. I'll also put in the description in Google Classroom at what time the 1.4b section of the video starts. So our goal today, I'm not going to write it in, I'll just verbalize it, is to understand basic function definition, notation, and begin applying to some different mathematical situations with functions. So there's going to be two examples that I use to help us understand the four rules and definitions of functions. The first two rules, I'm going to use this time versus temperature example, and then the next two I will also talk about another example that will help illuminate definitions like domain and range. So imagine, let's say we're somewhere on Earth and we're just standing in one spot, and we decide to take the temperature at every hour, 1 p.m., 2 p.m., etc. And we take the temperature at this single spot. We don't move at all. It's going to kind of be important in terms of making sure we understand the rules. And we receive the temperatures accordingly. 1 o'clock it's 100 degrees, 2 o'clock 110, and so on. And then we also have the graph here. Same data. Desert be a prime example of temperature changing, so much within a period of time. We could also connect them. Even though we didn't take the temperature at that time, we could connect them and get a general pattern from that. So the first rule we're going to look at is the relationship of inputs and outputs. So we see at 1 o'clock we have a temperature at 100 degrees. So I ask you the question, is it possible at 1 o'clock for us to take the temperature and to get two temperatures at once, and we're standing in one spot? So is it possible if we're standing in one spot and at 1 o'clock we look at the thermometer and we see two temperatures? No, that's not possible. We only have one temperature. Of course, maybe in some other spot it might be a different temperature, but that would be represented by a different function. So, or predictably a different function. So we're going to call the time that we selected as our inputs and the temperature our outputs. So at each input, we can only have one output. We couldn't have any more. So that's our first rule of a function. I'm going to try typing this. Let's see how this goes. For every input, and there is going to be a caveat to that. There is exactly one output. Now, that's true for every input a part of the domain, which we'll talk more about as we move forward. It's possible that for every infinite input that we could have, that we don't have an output. That just simply means we didn't take the data at that particular input. For our second rule, we're going to look at 1 o'clock and 5 o'clock. If you look, 1 o'clock has an output of 100, and 5 o'clock has an output of 100. 2 o'clock has a different output, so that makes sense that different inputs can have different outputs, but we also see at 1 o'clock and 5 o'clock we have the same temperature. And then we think about that realistically. Is it possible at different times for us to have the same temperature? Absolutely. If I stand right here, there's going to be times where the temperature is, for at least in terms of our observational approximation in terms of the data that we're taking, rounded approximate, that the temperature is exactly the same. So therefore, our second rule is different inputs can have, but don't have to, the same output. But the same input, or one input, cannot have different outputs, as we expressed within rule number 1. So those are our two main rules for a basic function. Functions make up a lot of real-life situations in terms of a relationship of an input and an output, or a relationship of 2 points of data. And we can expand on that in terms of specific type functions, which we'll get into later. But ultimately, those are the two guiding principles of a function. And for equations, whether we're talking about a quadratic or a circle, there are certain equations that can be functions and certain are not. And just because something's a function doesn't mean it doesn't represent a real life situation, but a function's a very important and useful tool in terms of evaluating a good amount of relationships between two sets of data. Okay, so the next two is going to be definitions, 3 and 4, and the first definition we're going to do is domain. And then the second definition that we're going to do is going to be range. So first off, let's talk about domain. Let's go to an example of a person being an input. I'll go ahead and write it down. I am going to erase it at some point, but just so you visually see it. A person being an input, and the output being having an ID, an Illinois ID. And this isn't realistic, but it works to help us understand the definition of domain and range. Let's say everyone living inside Illinois, so say if we got the nice state of Illinois here, beautifully drawn, everyone living inside of Illinois has an Illinois ID, and everyone outside does not have an Illinois ID. So let's imagine if I select, and what we want to do is figure out what people are a part of the domain of this function and which ones are not. So let's say I select someone living in Homewood or Flossmoor. Would they be a person that would have an Illinois ID? The answer is yes. Anyone living in Illinois ID, for simplistic purposes in this problem, has an Illinois ID. So the person living in Homewood, Flossmoor, or Chicago, or Schaumburg, where I live, or Springfield, etc., all of those people would be a part of the domain. But then if we selected some person of all the 7-ish billion people in the world from like Canada or Iowa or Hawaii or wherever, they are not living in Illinois. They do not have an Illinois ID, so they do not have an output. So they are not a part of the domain. So what we find is the definition of domain are inputs that have or produce outputs. Those are the values that are a part of the domain, inputs that produce outputs. And going back up to number 1, for every, where it says for every input, that's for every input a part of the domain. We know that there's exactly one output for every input into a function that is a part of the domain. And then now, very important point. Did we ask anything about the actual information on the Illinois ID? No. We just asked, if we were trying to determine domain, we just asked which inputs have an output or which people have an Illinois ID. We didn't ask anything about the information, and that's an important point in terms of being able to evaluate or determine the domain of a function as we move forward, that we're looking for the inputs that have outputs. We don't want to know anything about the information. And if we think about it in terms of numbers, like if I have an input-output table, we are just, or sets of data, we are just looking for the data that have an output. We don't want to look at what the data is, like if the outputs the driver's license number or the person's gender or birth date, something like that, or in terms of mathematics, what the value is of the output, like the y value of 2, 3, whatever. We just want to know if it has a y value. And then the range is fairly simple. That is simply what our outputs are. That's the actual data. That's saying whatever information. Now that we have some basic rules, 2 basic rules and 2 definitions for a function, we're going to look at function notation. So in terms of function notation, the special notation we use, which is right here, is read f of x or f at x. I typically say f of x, and that is a variable. That is our output, f of x. So when we write it, x will be our input, and f of x, it doesn't mean f times x. That all is a variable in itself, and that equals our output. So whenever they give you a value for f of x, like f of x equals 5, you think of that as your output. And then perhaps what we're doing is looking for the input. So for example, down here, starting just by evaluating functions, if they define the function as x squared plus 3x plus 5 and they say find f of 2, what they're simply mean is what's the function value at 2. If we think to the time temperature example, it means at a time of 2, what's the temperature? If this function is determining our temperature for us, or whatever it is determining, depending on the situation. So when I write this out, instead of plugging the 2 in right away, what I like to do is write out this function with open parentheses where the x's are, and then we can, if the input gets a little more challenging than just a number, then it can help us manage a little more challenging inputs, as we'll see as we move forward. So now I am inserting 2 in for there, and now I'm just going to simplify down. Two ways you can do this. You can keep writing f of 2 all the way down, or you don't have to write f of 2 on the left-hand side as you're simplifying, but do write it on the last line is preferable. So now we're going to simplify. 2 squared gives us 4, plus 3 times 2 is 6, plus 5, and then we add a cross, so we have 10 plus 5 gives us 15, and now we have our final answer. Now just note, why is this notation helpful? Now, since instead of y equals x squared and so on, if we have f of x equals, now in our final answer, we have the input value here and the output within the notation, nice, neat, compactified answer with both of those values. If we have y equals 15, then we would just have the output value. All right, moving on to the next page. Now I rewrote the function right up here just for instructional purposes, easy to see. Now instead of finding f of 2, we're finding f of x plus 3, which again, like I said, the inputs may get a little more complicated than just a number. They may be an expression like this where it has variables in it. So we want to make sure that we are plugging in correctly. Again, what I suggest is wherever there's an x, you put in open parentheses, leaving enough room for whatever you need to plug in. So here you see, relative to the last problem, I made these a little bigger because now I'm inserting x plus 3 in for x. Why would we insert variables or an expression like that into a function? Well, we'll see as we move forward. This time I'm deciding to not write the f of x plus 3. I'll just write the equal sign, which is fine as well, since we're probably going to need more than one step to simplify. X plus 3 squared, we did that in the prerequisite. That's x plus 3 times x plus 3. So x times x would be x squared. X times 3 is 3x. And then you have another 3 times x. So you have a 3x and a 3x as your middle terms. Add together be 6x. Again, you can go back to, I believe that was P4 in terms of squaring a binomial. And then the last terms of that would be 3 times 3, which is 9, plus... Now we're going to distribute the 3 in here, so we get 3x plus 9, and then plus 5. If you notice, this should be our last line, as I'll simplify it all here. So I'm going to write the f of x plus 3. If you notice, we really didn't need parentheses around here, because it's all in terms of addition and subtraction, but I wrote it all the same. Now we're going to simplify. You have the x squared, cross it off. And then you have a 6x plus a 3x would give you 9x. Cross those off. And then I have a 9 plus a 9 plus a 5 would be 18 plus 5 gives us 23. And there's our final answer for f of x plus 3. The next one is f of negative x, which I ran out of room, so I'll just do it up here. So now again, I'm going to rewrite the function x squared plus 3x plus 5 with those open parentheses. And now I'm substituting in negative x. Why would we do that? Well, we'll see as we move forward. So negative x quantity squared, that means negative x times negative x gives us positive x squared, and then 3 times negative x simplified would be negative 3x plus 5, and again I want to write the f of negative x over here as that's the last line. Now moving into determining different things, important aspects of a function from a graph. So if you look at the example up here, it says use the graph to determine the function's domain, the range, x-intercepts, the y-intercepts, and the function's values indicated below the graph. So for that last one right here where it says f of negative 1. So let's start out with domain. Domain again means inputs that have outputs. So inputs would be x values like this, -3, -2, 1, 0, 1, and so on. So if I draw a vertical line right here, every single x value on this vertical line is -4. Every single x value on this line is -3. I'll be more specific. This is -3, 0, -3, 1, -3, 2, -3, 3. You see the y values changing because we're going up and down, but the x values does not change. So if we want to determine domain, what we're going to do is find all the inputs that give us outputs. Remember, we don't need to know what the output is, just that it gives us. So I want to look at all the x values. So I'm going to start down at -infinity. And if you look, this won't intercept the graph because we do have points here, not arrows. If we had arrows, that would mean it would go on infinitely, and then it would. So I'm going to keep drawing vertical lines. You can do it kind of like I am, but imaginary. You're going to draw vertical lines until the first vertical line that intercepts the graph, which is right there. And I want to ask, what is the x value that gives us that y value? The y value is 6. It doesn't matter what that y value is. What's important is what the x value is. So the first x value that gives us an output is -2. Therefore, -2, since it gives us an output, is a part of our domain. If I continue drawing vertical lines continuously, you see I have no breaks in the graph until I get up to here. And the x value here is 6. So our x values that give us outputs go from -2 to 6. And we're going to write it in interval notation. Interval notation starts at -2, comma, goes to 6. They have brackets on them. If you recall, bracket means it's equal to or a closed circle, because you have an output at that value. An open parentheses is equivalent to an open circle, which means there's no output there. Note negative and positive infinity. Negative and positive infinity will always have an open parentheses, either beginning or ending. The reason is infinity is a concept, not a specific value, so it cannot equal that value exactly, hence why we have parentheses, and interval notation is preferred. So now we're going to look for B, we're going to look at the range. So if we did a vertical line to find the domain, we're going to do a horizontal line to find the range, because if I draw a horizontal line, for instance, right here, our y value here at every single point is -3. And more specifically, let me demonstrate. 0, -3, 1, -3, 2, -3, 3, -3. If you see, the x values change as we move left to right, as x values do change, but the y values don't change. So if we want to find the range, which is simply what are our outputs, and again, it doesn't matter how many there are of those outputs, just if we have them, we are going to draw a vertical line, start down at -infinity for y, and go up until we intercept the graph, which would be right here. And right there, our y value is -2. I'm going to continue up. Actually, I'll go ahead and write, so B, our first y value is at -2. And we're going to continue up, no breaks in the graph until we get to this point, and our y value right there is 6. Note, if there are breaks in the graph, I believe we'll see what that looks like. No, we will not. What you do then, if there's breaks in the graph, you end it, and then you put a union sign that looks like this. So if, let's say, we had a break in the graph, let's say for this graph, let's say we had an open circle right here at the y value of 1. At the y value of 1, let's say we have a break, we would go -2 to 1. It would include 1. Or no, it wouldn't, sorry. So it would have an open parenthesis. Union means or, and then we continue on at 1 until we got up to the last value of 6. That's what a domain would look like if we have a break in it, which we'll look at more as we move forward in homework, in questions in class, and so on. Next question is C, the x-intercept. So we're going to go, where does this graph cross the x-axis, which is right there, and that's at the coordinate 4, 0, or you could write it as x equals 4. D is the y-intercept, so we come up here, the y-intercept is 0, 4, so you could write it as 0, 4, or you could write it as y equals 4. I prefer the coordinate, so we don't think, for instance, it's the equation of a vertical or horizontal line. Next, we have I believe it's a function at the given value. Yes, so the next thing we want to find is f of -1. So we go to the input of -1, and we go, where is it cross where does we produce an output at the x value -1, so where's this vertical line across the graph, which is right there. So the function, so the way we'd write it is, let's see, I got to come over here to e. So f of -1 equals, I believe it was 5. Yes. So f of -1 equals 5. So now we're going to do the same for this problem. Domain, start out at -infinity, and if you look, we have an arrow. That means this is continuous on infinitely, and it looks like it's going to go vertical, but it never will go completely vertical. As a parabola, it never does that. As you see, this is a parabola, so that means at -infinity, we actually do have an output. We don't have any breaks in the graph, and then this would also continue on to the right and down, but more particularly for domain, we're concerned with moving to the right. So there's no breaks in the graph. All inputs give outputs, so if that's the case, then the domain is -infinity to positive, and oops, I forgot to write D first, which if you didn't on your homework, I wouldn't take off for that, but it is important to be aware of that. Rating D : stands for domain for when you take quiz. Okay, so now the range, we're going horizontal line starting at -infinity, and this goes down to -infinity, so it would intercept the graph. And note, we have two outputs, for instance, at -3, -4, and so on, but that's fine because different inputs can have the same outputs. And we're not listing how many of those outputs we get when we list domain. We're simply listing what are the outputs. So -infinity all the way up until the vertex right here, which is at the y value of 4. So our range goes from -infinity, remember we use parentheses for -infinity, up to the y value of 4. C is x-intercept, so we're going to look where it crosses the x-axis. It crosses right there at -3 and +1. So we can write that as -3, 0 and 1, 0. Again, I prefer coordinates. D is the y-intercept or intercepts, and for a function, it should only have one y-intercept, because if it intercepted, let's say, if a graph went like this, and intercepted the y-axis in 2 spots, then it wouldn't be a function because it wouldn't pass the vertical line test. Of course, we'll talk more about that later. Y-intercept is right here, and that y value is 3, so the y-intercept is the coordinate 0, 3. And then the last part is evaluate at these two values that are asked for. The two that are asked for is -2, which is right here. That has an output of 3. And then at +2 has an output, looks like -5. So I'm just going to write it right over here so I can see the graph. So this is your answer for E, -3, 0. And then at the f of 2, oops, sorry, we want to write it as a coordinate. My bad. Or not as a coordinate. I wrote it as a coordinate. We want to write in function notation. F of -2 equals +3. And then f of 2 equals, let's look just one more time, -5. Don't worry about the last problem, number 3. We'll talk about that in class.